Hello and welcome to Calculus 2, Math 112. This is our fourth lecture, which is going to focus on the concept of work. Now, work is an extremely important concept in physics because it is connected to the concept of energy. And whenever we're looking at the conservation of any energy which is contained in any example in which forces are being applied, there's a velocity and acceleration, motion, and so on. In such a case, if we want to look at conservation of energy, we need to know about work, which is equivalent to energy. Generally, we think of work as a force applied through a certain distance, and that is how we will define it mathematically. So suppose we have a force of 10 newtons applied to an object, and we move the object 6 meters. The distance we move it is 6 meters. Then the amount of work that is done is 10 times 6, which is 60 Newton meters. So now we have a new unit of measurement, a joule, named after the physicist who did a lot of work in this area. A Newton meter is a joule. And we know then this particular unit expression reminds us that work is force times distance. Now suppose that the force is not constant, because in our previous formulas we were assuming that the force was a constant value. Now the force is going to change. It's going to be a variable force over a particular distance which is traveled, and the force will change in value according to the variable x. So the limits for the distance traveled are x limits. X goes from A to B. And now, since x is infinitesimal in its value for force, we can actually write that work is the integral from A to B of f of x dx, where f of x is the variable force, and x is the variable we're using for the distance measurement. Now, one of the most important and most commonly used formulas for force in order to calculate work is Hooke's law for springs. If we're dealing with compression and stretching of springs, the force is equal to kx, where k is a spring constant, varies from spring to spring, but is constant for a given spring, and x is the distance variable, and f is the force variable. And so now we see a particular example of a variable force, and we're going to calculate the work. Suppose that we have a variable force, f of x, which equals the square root of x plus 1 for x between 1 and 5. If we want to find the work done on that interval, we just integrate f of x dx over those limits, 1 to 5. F of x is the square root of 1 plus x. If we integrate that, we get 1 plus x to the 3/2 times 2/3 from 1 to 5. So our final answer then is going to be 6 to the 3/2 minus 2 to the 3/2 times 2/3. That is the total work done for f of x equals the square root of 1 plus x on the interval from 1 to 5. Also, let's recall that if f of x is in newtons and x is in meters, then this work is in the unit of joules. Now let's take a look at another example. In this case, we have a spring. The spring force is f of x equals 10x. That means that 10 is the spring constant, and in this case we're going to let x go from 3 to 7. So the compression, if we were working, let's say, in meters, would be from 3 meters to 7 meters. What is the work done in compressing a spring from 3 to 7 meters if the spring constant is 10? So we just integrate f of x dx. And let's add in our dx right here. Very good. And now, if we do that, we get 5x squared. And if we go from 3 to 7, our upper limit is 7, lower limit is 3, we get 200. So if we're working with units of newtons and meters, we have a work of 200 joules. If we write the work in general for a spring force, the work is the integral over the limits a to b of kx dx, where k is the spring constant. If we integrate that, we get k over 2 x squared from a to b. So essentially now we have a new formula that if we're compressing a spring from a to b, the work done is just 1/2 k b squared minus a squared. And that's a general formula that can be used without having to integrate the force. This concludes our lecture on work. Thank you for listening.